All right, guys, so let's get started. We'll do a few problems. I'll do the slightly harder ones, okay? I want maybe one or two easy ones. Okay, so what are the following temperatures on the Kelvin scale? Okay, so let's say we'll do this one, or we'll do this one. Okay, so whenever you have the temperature in the Fahrenheit scale, you have to first convert it into the Celsius scale and then to the Kelvin scale. Okay, so and temperature on the Fahrenheit scale is related to the Celsius scale like so. So temperature on the Celsius scale is Fahrenheit scale minus 32 divided by 5/9. Okay, so here is roughly the rule of thumb. If you have a temperature on the Fahrenheit scale, subtract 30 from it and then divide by or multiply by half or divide by 2. So here's a quick, so 72 degree Fahrenheit, 72 minus 32 would be 40. 40 divided by 2 would be 20. Yes, so that's a quick calculation. Okay. So 5/9, 134 minus 32. Okay, again, so and so the temperature on the Kelvin scale is plus 273. Fifty 32. Three 30 39. Okay, so what we found was, what we are saying is 134 degree Fahrenheit is 56.7 degrees Celsius is 339.7 Kelvin. So here is the temperature on the three scales. Okay. And so that's in Death Valley. We'll do a problem, and we had a seminar about this not too long ago, but apparently if your body temperature gets to 44 degrees Celsius, it's mostly goodbye. And all kinds of stuff happens. Yeah. At 40 degrees Celsius, bad stuff starts happening. Okay, how large an expansion gap should be left between steel rails if they may reach a maximum temperature of 35 degrees Celsius greater than when they were laid? The original length is 10 meters. Okay, so here in Daytona Beach, you see a temperature rise that much. In the winter, you can get 0 degrees Celsius, and in the summer, you'll get 35 degrees Celsius. Yeah. So you would see that temperature rise here. Okay, so here's one rail. Okay, the gap you want to leave is the room for each rail to grow. Yeah. This is 10 meters. Okay, so you saw that the increase in length is original length times rise in temperature times alpha. Yeah. And alpha for steel yes, so Steel, it's 12 times 10 to the minus 6 per degree Celsius. Okay, so the increase in length for each rail would be 10 meters, 35 degrees Celsius, and 12 times 10 to the minus 6 per degree Celsius. So this would be 2, 3, 10 minus 3, so 3.5 times 1.2 into 10 minus 3 meters, and that's a millimeter, so this is a 3.5, 1.2 is 4.2 millimeters. That's half a centimeter, about that much gap. Okay. All right, this problem is the following. Let's say this is the ocean. Okay. And what we'll do is we'll look at a column of water, and as you warm the ocean, the volume of this thing will increase, and we'll assume that it cannot expand that way, so all the volume increase will happen in this direction. Okay, so the problem is about if you warm the ocean by 1 degree Celsius, how much would sea level rise? Okay, so that's the issue. That's what the calculation is about. So global warming will produce rising sea levels, partly due to melting ice caps and partly due to the expansion of water. So we are calculating the sea level rise because of expansion. Okay. To get some idea of the size of this effect, calculate the change in length of water 1 kilometer high. 1 kilometer high. The average depth of the ocean is about 4 kilometers. Okay. So, and the warming is 1 degree Celsius. Okay. Now, if you guys can check this out, the increase in volume is original volume times beta times delta. Yeah. And the original volume is area of cross section times height. And increase in volume is area of cross section times delta height. So the increase in height just from the volume expansion is beta times h times delta t. So let's look up beta for water. Here's the expansion coefficient. Volume expansion coefficient for water. All right. So beta for water is 207 times 10 to the minus 6 per degree Celsius. So the height would be 207 into 10 minus 6 and 1 kilometer, and temperature rise is 1 degree Celsius. Yeah. 207 into 10 minus 6 kilometers. Uh-huh. This thing?
No. Very bright. Yes.
That's the change in temperature. Delta.
Okay, at the T.
Yeah.
Okay.
All right, so that's 10 to the 3. So that makes it 10 minus 3. 10 minus 3 meters is millimeters, so that's equal to 207 millimeters. That's about a foot, 2/3 of a foot, 20.7 centimeters. Mm-hmm. Yep.
Why could you not just use the change in length formula?
I'm sorry?
Why could you not just use the change in length formula for the ground?
The volume is increasing.
Oh, we're not looking for the volume, we're looking for the height.
So, okay. In this formula, when you talked about the rail, when you raise the temperature, the width of the rail was increasing, and that was also increasing. Okay. You let the width increase here, and so the length didn't increase as much. In this problem, what they tell you is this side of the ocean is pushing, so the width is not able to increase. So all of the increase in volume is going up there. Okay. So if you let this increase, then the length would increase by 1/3 the factor. So you're not letting it get fat, you're only letting it get taller. Yeah. So again, the expansion is not that much, but most of the sea level rise would come from melting of the glaciers. All right. So, okay, when are breezes possible?
Breeze.
Yeah, when can you have a breeze?
When the water from the ocean heats up and the air rises.
Okay, so you can have breeze when differential heating happens. What that means is you're putting the same amount of energy in two different substances, and if their temperature rises by different amounts. Okay? And their temperature, when will their temperature rise by different amounts? If the temperature will rise by different amounts if their specific heats are different. You're putting the same amount of heat, okay? So that's what this problem will illustrate. Okay? So to have a breeze, you were 2 steps ahead of me. To have a breeze, you have to have pressure difference, and the only way you can generate pressure difference is differential heating. Okay? All right, so what we'll do is we'll do this for water and concrete. just to illustrate. Okay. So the same heat transfer into identical masses of different substances produce as different temperature changes. Calculate the final temperature when 1 kilocalorie of heat transfers into 1 kg of the following, originally at 20 degrees Celsius. Okay, A, water. And so 1 kilocalorie of heat, mass is 1 kg, and specific heat is, for water, is 1 kilocalorie. I know this number, per kg per degree Celsius. So the kilocalorie cancels, the kg cancels, so the rise in temperature would be 1 degree Celsius. So for water, for a kg is, this is half a kg, twice this water. If you dump 1 kilocalorie of heat on this thing, you'd raise its temperature by 1 degree Celsius. Let's do the same thing for concrete. Of course, the specific heat of concrete is much lower, so the temperature rise would be much higher. Okay. Specific heat of concrete in calories per gram per degree Celsius. Okay, it's 880 joules. So you see, it's 5 times less the specific heat, so the temperature would rise to 5 degrees Celsius. All right. So, and that's what would happen to dirt. Okay. So you have a parking lot next to a ocean, you'll always get a breeze. So we built some parks along our beaches, and that's concrete next to the ocean, so you can have a microclimate there. All right, so here is a problem about heat stroke and all. Following vigorous exercise, the body temperature of an 80 kg person is 40 degrees Celsius. Okay. At what rate in watts must the person transfer thermal energy to reduce the body temperature to 37 degrees Celsius? So that's your normal body temperature roughly. In 30 minutes. Okay, so you're trying to cool down in 30 minutes. And I mean, in 30 minutes, you could still have damage. In 40 degrees Celsius, you feel dizzy and all that kind of stuff. assuming the body continues to produce energy at the rate of 150 watts. Okay, so what we're going to do is how much heat you need to remove from your body to cool down from there to there. We'll first calculate that. And then you have 30 minutes to get rid of that heat. Okay. So here's the amount of heat. There's your mass. There's your specific heat times the change in temperature. Okay. Now, you're essentially water, a bag of water. Okay. So specific heat of humans are essentially water. So we'll assume the specific heat of water, joules per kg per Kelvin. And per Kelvin is the same as per Celsius. 1 degree Kelvin is the same as 1 degree Celsius. Okay. And you want to reduce your body temperature by 3 degrees Celsius. Okay, so this is how much heat you have to reduce or get rid of. Okay, essentially 1,000,000 joules. And so power is Q over T. Okay, if you're going to get rid of it in 30 minutes, so there's joules, 30 minutes into 60 seconds. Okay. 560 watts. Okay, but your normal bodily reactions are producing 150 watts, 150 joules per second. So your cooling system has to get rid of, so power total is 558 plus 150 watts. That's the rate at which you have to get rid of heat. Okay, that's 708 watts. Essentially, you got to increase your cooling rate by 400% for half an hour. Yeah. This is what happens to football players practicing in the summer. Yep. I'm sorry? Yeah. Okay, so we'll do an experiment like this, a calorimeter. So this is a science, a calorimetry. I don't know, do you guys do a calorimeter experiment in your chemistry classes? All right, so 1.2 kg sample of water at 10 degrees Celsius is in a calorimeter. You drop a piece of steel with a mass of 0.38 kgs at 215 degrees Celsius into it. So you drop this in here. What is the final equilibrium temperature? Okay, what happens? This guy loses heat to the water. Okay, so make reasonable assumptions that the steam produced condenses into liquid water and so on. Okay, this thing loses heat and that guy gains heat. Okay, so Q gained, that's the heat gained by water, that's positive, and heat lost by the steel is negative. And if you don't lose any heat, which is your goal, then to the environments, okay, then those two should add up to 0. Okay, mass of water, specific heat of water, rise in temperature of water, plus mass of steel, specific heat of steel, change in temperature of steel should equal 0. Okay, change in temperature of water is it's always final temperature minus initial temperature plus mass of and final temperature minus initial temperature. Okay, the final temperature will be lower than that, and you see this will be negative. This will be higher than that, that will be positive. Okay? All right. So and again, I'm not putting a whole bunch of units and stuff. So for water, it's 4.186, and for steel, it's 448.
4186.
Mm-hmm. And you can see that these units will cancel and you're left with Celsius. So this temperature, these units cancel, okay? So 16.4 degrees Celsius. Okay, this problem also illustrates the following. You see, there is the specific heat of steel. There is the specific heat of water. It's almost 10 times greater. Okay. And the temperatures, so the final temperature is that. So the water went from 10 degrees Celsius to 16.4 degrees Celsius. And the steel went from 215 degrees Celsius to 16.4 degrees Celsius. Yeah. It's very hard to change the temperature of water substantially, a body of water substantially, because of its high specific heat. Okay. That's why waterfront property is expensive, besides being pretty as well. Yeah. Okay, so if you have an oil spill and it catches fire, it's very hard to put out the flame. Okay? And this problem illustrates that. All right, so it's difficult to extinguish a fire on a crude oil tanker because each liter of crude oil releases, so when you burn 1 liter of crude oil, it releases 28 million joules of energy when burned. So to illustrate the difficulty, calculate the number of liters of water that must be expended to absorb the energy released by burning 1 liter of crude oil. So if the water's temperature rises from 20 degrees Celsius to 100 degrees Celsius, it boils and the resulting steam's temperature rises to 300 degrees Celsius. Okay, so what this is saying is you have 1 liter of oil, you burn it, you're releasing so much heat, and now you're going to use this heat to heat the water, boil it, and then raise the temperature of the steam. So in practice, what you're doing is, here's in the ocean. Well, here's the problem. You have a spill in the ocean. What happens to the oil? It spreads. So the area is huge. All that oil is exposed to the oxygen. It catches fire. So here's the oil spill. You're not spraying water from here. You're spraying from here, from the outside. You have problems. Okay. All right, so what we're going to do is, here's the heat that you have from burning 1 liter of crude oil. That's how much heat you have. What are you going to do? You're going to take a mass of water, warm it from 20 to 100 degrees Celsius. And then what are you going to do? Then you're going to vaporize it, make it into steam. Then what are you going to do? You're going to warm same mass. You're going to warm it from 100 degrees to 300 degrees Celsius. So the question is, how much water can you do that to? Okay, so let's look up all those numbers. Q is 2.8 into 10 to the power 7 joules. We already know the specific heat of water, 186 joules per kg per degree Celsius. You warmed up the water by 80 degrees Celsius. Okay. the latent heat of vaporization for water. .26 times 10 to the 6. All right, specific heat of steam is 2010. Okay. .34 kg. And the density of water is 1 kg per liter. Okay, so volume of water you need is 9.34 liters. So to put out a fire for 1 liter of crude oil, you need 10 liters of water. And that's assuming the steam gets to that temperature. Of course, if the steam blows away, it's not getting to that temperature. You're needing more water. So all these fires are put out by how?
Well, there's also like water doesn't want to sit on top of oil.
Right.
So like that's how it usually soaks in, goes on top. So that's why they usually use dry propellant or dry extinguishers.
Yeah, you're trying to get rid of, you're cutting off the oxygen.
Yeah, but you can't use those in water because they're all toxic.
Oh, yeah?
The dry propellants. That's what they're using, like Corexit. During the big Gulf one, they're using Corexit because it makes the oil fall.
Mm-hmm.
So it becomes more dense, it binds to the oil, and then it falls to the bottom, but then it just recycles and poisons everything for like 100 years instead of 5.
I see. So just shove the problem to the future generation.
Yeah, that's what they're governments do. Most of the time.
So you have experience with these things?
Oh, yeah.
Oh, yeah? All right, so maybe we'll do one more problem. This was interesting too, but that's a long one. Okay, so it turns out that air is a poor conductor. The problem is if it blows away, then, so you warm, so let's say here's your body, and this air would act like a blanket because it's a poor conductor. It's just that you would warm this, and then if this air blows away, then it gets replaced by cold air, and then you start losing heat. How do you prevent it from blowing away? I'm sorry? wear multiple layers. Okay? And that traps the air. But if you're a bear, what you do is you have fine hair that, or any animal. So their closest layer is fine hair that traps air. That's the deal. Okay? And you want to make sure that, well, if you're a penguin or stuff, that it doesn't get wet. Okay? So, so what is the rate of heat conduction through a 3 centimeter thick fur of a large animal? So essentially, and you'll see in this problem, having a 1.4 meter square surface area, which is roughly, well, a little greater than ours. Assume the animal's skin temperature is 32 degrees Celsius. So if you don't want to lose hair, what is another thing you do? You cut off blood flow to your skin. Okay, so that's why here the temperature is lower. The air temperature is -5 degrees, and the fur has the same thermal conductivity as air. So you see that? So the idea of the fur is essentially just trapping air and thermal conductivity of air. What food intake will the animal need in 1 day to replace this heat transfer? Okay. So thermal conductivity times the area times the temperature gradient. Okay. So the rate of heat flow, thermal conductivity of air, we don't have a, what is the thermal conductivity of air? Is watts per meter per degree Celsius. Area is 1.4 meters square. And temperature difference is 32 plus 5, 37 degrees Celsius. And 3 centimeters. Okay. So the rate at which you're losing heat is so when animals hibernate, they want to reduce the temperature difference. You're lowering your body temperature, so you're reducing this number. You're losing less heat. And how much do you need to reduce heat? Your body temperature. Let's say you have 1,000,000 joules of stored fat. You gotta make sure that the 1,000,000 joules lasts 4 months. I guess so. That's how evolution works, or you just make sure that you have enough store. So that's the kind of calculation that goes on. What's that?
His arm squeaks on the desk and it sounds like a little fart every time. I just can't. I just can't.
Okay, so what food intake will the animal need in 1 day to replace this heat transfer? Okay, so you're losing that much heat. Okay. So the amount of heat lost is Q over T times T. And in a day, 24 hours. And so you're losing 1,000 kilocalories per day. A kilocalorie is a food calorie. So half your food your day's requirement. So if you want to hibernate for 40 days, you'd better have store of, well, for a bear, I don't know what the calorie requirements are for a bear. Tell 'em.
I don't know the exact calorie, it's between 50 to 100 pounds of fat though.
Okay. How many calories does a bear eat each day?
Oh, you mean, I didn't.
5,000
Yeah.
calories.
Yeah, I thought it was like,
It's between 5 and 8.
Yeah.
it's like 60% of their body weight.
Yeah.
What?
Yeah. Like,
No,
that's-
no, no.
Like,
So they're herbivores and eat mostly like fruits and insects.
All right, so anyway, so for 5 days of hibernation, you got to eat 1 day of food. So you have to have 1 day of extra. So if you're hibernating 5 months, you have to have stored enough fat that you would have eaten in 1 month. That's what that means.